How's it going? This is Will doing Lab 2, Charge Tapes, continued. So, Lab 2 is basically a follow up to Lab 1 where we're looking at the same system of a piece of tape levitating another piece of tape of the same charge, we're assuming. And so the purpose was to find the magnitude of the charge on one piece of tape, assuming the charge is evenly spread across the entire length of each tape. So many point charges. So we're no longer considering each piece of tape as just one point charge. So the results, as you can see here, the magnitude of this charge in Lab 2 was larger than the magnitude of the charge found in Lab 1. So fundamental physics principles are the same as before in Lab 1, where we have Newton's second law as our main thing, where we're saying the net force is equal to 0 because it is in equilibrium, where the force of gravity is equal to the net electric force pushing up. So and the gravitational force is pushing down. So they cancel out to be 0. So with net electric force, we use Coulomb's law, where just say it's a K, which is the Coulomb's constant times charge of one times another charge times the unit vector of the position vector, and divided by the magnitude of that vector squared is just the force of the electric force. And so force of gravity is just the mass times the gravitational constant. Initial conditions. So the system are the two pieces of tape, and the surroundings are everything else. The length of each tape was around 0.2 meters, and the distance levitated was about 0.04 meters. And the mass was 2.1 e to the negative fourth. UFPES is just the Coulomb's constant, and G is gravitational constant. The real difference here was just using Q equals 3.356 e to the negative eighth coulombs instead of the one from Lab 1, the charge from Lab 1. So we had to define some functions for this computational model. So same as last time, we had to define the E field. So this is literally just the same thing as Coulomb's law, just without one of those charges there. So it's just KQ divided by UFPES times Q times R divided by the magnitude of R cubed. We also defined line charge, which this is saying that for each piece of tape, we're just considering a line. And we're dividing that tape up by n number of segments, and each segment has the same or equivalent amount of charge. So this is literally just a function to do that for our tape. So we can plug in our values or our inputs there for each piece of tape, and that will get it. So for this lab, I used n equals 100, by the way. Okay, so finding electric force in the E fields at each segment, and we're saying each segment is just dq. So basically, we just iterated through for each segment of the top tape. We then iterated to find the E field from due to each segment of the bottom tape on that segment on the top tape. So for every segment on the bottom tape, and summing that up to get the E field of that segment of that particular top segment, and then also finding the electric force. So, but actually the net electric force over time. And so that's just all this is. So as a result, we found, under the assumptions of no air resistance, that each piece of tape had the same charge, and that charge was spread evenly across each tape. Found that the magnitude of the electric force and the magnitude of the gravitational force, to get them to be about the same, we needed the magnitude of the charge on one piece of tape to be 3.56 e to the negative eighth coulombs. So this was just through trial and error. As you can see, this blue line is the bottom tape. You can't really see it, but there's a red line. It's just the top tape. These green arrows are the electric fields at each segment, so there's 100 of them. And then FGrav pointing down, the yellow arrow, and then the white arrow is the net electric force pointing up. So now we can get on to the discussion. So what if we had modeled each tape as a single point charge like in lab 1? Well, we did. So the magnitude of the charge was less than the magnitude of charge we found here. So why is that the case? Why do these differ? And which value is more likely to be closer to the real value? So they differ because the iterative sum of a bunch of forces is much more precise than using only one point charge. The many point charges help account for the spread of Q, so where Q is spread across the entire length of the piece of tape. And we know that as you get further from the center of the tape, the electric field caused by that charge gets weaker because basically because it's a larger distance from that center of the tape. Um, and so, therefore, it makes sense that the magnitude of the charge for this lab was larger than in Lab 1 to account for the loss in the effect of each, or the effective, the effect of each piece of charge for each segment. So, in conclusion, there were some potential sources of error. We did not take into effect charge losses to the environment. Also, the distance the tape was pushed up was not measured very precisely. Also, our assumptions could have been false, where, we didn't take into account air resistance. We assumed that the charges were equal for each piece of tape. They could have been different. And also that they were spread uniformly across, the charge was spread uniformly across each piece of tape, which it very well could have not been. So yeah, so that is everything, but thank you very much.